ठीक है, स्टार्ट कर दीजिए। Okay, so we start and we'll continue our discussion. We had started the symmetric members in pure bending. Now, if you recall, I don't know if it was covered in your APL 100 or not, the forces which we got when we had a section, we call them what? Shear force and bending moment. So, we are talking of that same bending moment here, and a moment when it acts on a thin member, it has three components. A component which is along the axis of the shaft, and what sort of a deformation will that moment do which is parallel to the axis of the shaft or which is acting along the axis of the shaft. If I look at this shaft, moment which is along the axis of the shaft is what we have seen in chapter 3. It will tend to twist the shaft. But if I look at the two perpendicular components, that being the y component of moment and the z component of moment, two components, each of these will try to bend this shaft. One of them will try to bend it about the y-axis, the other will try to bend it about the z-axis. So if I have this shaft, maybe I should have got something more, this thing. Let's see if I have some. So I don't want to break the pen, so I will use this. A twisting moment will tend to turn it like this. Bending moment, of course, this is a brittle material, so this doesn't bend. But it will tend to either bend it on the top, or if it is along this axis, it will tend to bend it either towards me or towards you. So physically, that is what bending moment does. So maybe as a corollary, let's write this. So we have a thin member which we call as a shaft, rod, whatever name. These my and mz, as I said, they are referred to as the bending moment. Okay. So now so this probably was the motivation. Now we look at What I mean by pure bending is that if I cut a section, the only force coming at that section is a bending moment about one of the two axes, and here the bending moment is acting about the z axis. Okay. So, pure bending implies a section through if we look at a section passing through C. So, let me call this as A, call this as B. So, I cut a section at C, and then what I find is that the only external it should actually be not external. If I am cutting it at the internal section of the beam, what I get, it is external to C, but it is internal to the rod. So, the internal force which comes in on at section C is just a pure moment M. Now, we have this AC, this is undeformed. Due to action of M, so M tends to this moment M, the way it is applied, it tends to curve the bar upwards. Okay. I have this, I try to apply this, it will tend to curve it upwards. Now, as shown, that means C is a positive face, direction of M is counterclockwise. So, M is termed as positive. So, on a positive face, if M is counterclockwise, then we call it as positive. And a positive M tends to bend the bar concave up. Yeah, थोड़ा स्लो लिखे. ओके, ठीक है. Okay. So, now what we will do is, let us try to analyze. I draw a blown up picture of the face, and here now on this face, this is I look at the side view. Now this is a symmetric bar, so xy is the plane of symmetry. So it has to be symmetric about this line. So we draw a side view like this. And then in this side view, let me try to show what are the different forces acting on an element. So I choose an element like this. On this element, we will have all the sigmas and taus will act. And what I'm going to do is, to make it more clear, I will draw 3 elements and show only one of them on each of them. Actually, at each point, sigma is acting, tau xy is acting, tau xz is acting. Or tau, it would be the other way around, tau yx and tau zx. This is the x phase. Okay. So, let's see. So, there is a so this what I'm showing are the cut. If I cut a section, then the different traction forces on this cut section, which is an x phase, there is a sigma x dA, and then I draw another section. A shear force tau zx is going to act there. So that I show on a different phase, and on a third phase, I will show tau. Now this is x phase tau yx. Now, of course, in books you may find tau xy or tau xz. That does not make a difference. This is a symmetric case, and sometimes notations are different. But these are the 3 external forces which will act on this phase. Now, so if I calculate forces and moments on the face, that means I have to integrate over the area. So, what we will have is if I integrate all the x forces, I'll have to do an integral sigma x dA on the entire area. And this will be equal to f sub x, and this is 0. Because there is, on the cut section only I have a moment. So, integral of sigma x dA will be 0. Similarly, when I try to calculate so this also tells you if there is a tensile force also acting, then integral sigma x dA will be equal to fx, whatever the tensile force is. So, later on when we do a combined case of extension force, a tensile force and bending, then integral sigma x dA will become equal to fx. Right now it is 0. Okay. Then if I calculate the moments, then if I want to find the moments about the z axis, now I am exceeding my this thing. I'll come to this argument in a bit later, but I will show that by geometrical arguments tau xy and tau xz will be 0. By symmetry and geometry, tau xy and tau xz are 0. And this I will show in a minute. These two things will be 0. So now when I calculate the moments, recording. So when I calculate the moments about the z axis, then the only thing which will contribute to moments about the z axis will be sigma x. And let's see. So sigma x will mean it will be moment will be equal to yj cross sigma xi d. And once again, to look at this, if sigma x is the only force acting, I have to calculate the moment about this. So I'll take yj cross sigma xt. So what I get from here is integral of minus y sigma x dA is equal to m. M is about the k direction. So when I do j cross I, it's a minus k. So minus y sigma x dA is equal to m. So, and integral tau xy dA obviously will be 0. So, and integral now if we look at figure of the couple M which we have, this acts on the plane of symmetry. So the member will bend but stay symmetric with respect to xy plane. So as the member bends, it stays symmetric with respect to the xy plane and it bends uniformly at all sections. So what would you expect would be the shape of this line AB? So the line AB which was at the top here. Its curvature, because at each section the moment is the same. So when it bends, the curvature is the same at each section. And if the curvature is the same at each section, this will tend to turn into a circular arc, because the same moment is acting at each section. So its effect of deformation is the same at each section. So any cross section, so what we can therefore from here what we can get is any section, cross section perpendicular to the axis stays planar. And the plane passes through C, the center of curvature. That means if I have so there is a center of curvature C, and the straight member AB bends into a shape of a circular arc under pure bending. And that's why we start all our discussions with pure bending, because then we can make this assumption of a uniform curvature and a circular. Now, on the surface of the member, sigma y, sigma z, tau yz will be 0, because the only force which is acting is just this bending moment. So therefore, there will be no sigma y, sigma z and tau yz. And this also follows from the deformation that plane members will stay plane. So because of this now, these forces are, or these components of stress are 0, they are 0 on the surfaces. So therefore, inside also, if there has to be a continuity, they are 0, because there is nothing which is causing these forces. So the only non-zero element of stress in these bars is equal to sigma x. See, there is another argument which goes, that is, if you have if I look at two adjacent elements, and if the element BE deforms, see, this is to show that planar elements stay planar. If suppose BE curves, it will curve either outside or inside. Suppose it curves outside. But then if I look at BE on the right side, if that also will have to curve outside. So that means if the two of them curve outside, the geometric compatibility will not be there. Because, so if this element AD and BE, if they are curving outside or inside, and the neighboring element will also have to curve the same way because there is the same loading on that. So then there will be a gap or there will be extra material, so that compatibility is not there. Therefore, they stay straight. So this is the argument to show that they stay planar. And because of this, the shear stresses in those directions become zero. And that is why the stresses also become zero. Because they cannot deform, they have to stay planar. So now that means the state of stress, if this is like this, so this was the member. So what sort of a strain? There is only sigma x here. What sort of a strain will we see here? So firstly, let's look at strain coming directly because of the stress. And the Poisson's ratio or those things we'll see a bit later. So now there is only sigma x. So what will happen? The strain will also obviously, this is, and also from the geometric argument, you see initially this was straight, everything was straight. Now this is curved into a circular bar. So what do you think is happening as far as across the cross section? If I move from, what did I call this? Was AB. If I move from B to D, what is happening to the elongation, or how is this getting deformed? If initially everything was equal, what is happening to the section at AB? Is it elongated or is it less than the previous length? See, initially everything was a straight line. Now the same material has got curved. So what is going to happen is, portions in the top half or somewhere in the top, they are getting contracted. The strain there is negative, whereas on the bottom side, they are getting elongated. Because earlier everything was a straight line, now it turns into a circle. So the bottom part, at least some part in the bottom, they will get elongation. And the top part will get contraction. So because of this, top part of the beam sees a contraction and the bottom part sees an elongation. So if I look at the strains, somewhere along the top of, I have drawn some arbitrary line, I have not defined what it is, but I am assuming that line is the one where the length does not change. And above that, we will have contraction for the given loading, where M is positive, and there will be an extension. So now what we have is a state of impure bending. The member is in a state of आज कोई होमवर्क ड्यू था? नहीं, देयर इज अ होमवर्क ड्यू टुडे. ओके, वो चला गया तो होमवर्क तो दे जाए. तो देयर इज अ state of uniaxial stress. If we look at the stress, we'll collect it at the end, so don't worry. There's a state of stress. We have seen uniaxial stress earlier also, but those cases were more straightforward because it was a uniform stress across the cross section. Here what we are seeing is there is a state of uniaxial stress, but the stress is not uniform across the cross section. It is having some distribution, which we will see what it is. Okay? Is that fine? So now what we show is that there must be a surface parallel to x-axis where epsilon x is 0. We had epsilon x which was negative on the top part, positive in the bottom part. So there must be some part where epsilon x must be 0, and we call this surface as the neutral surface. And on neutral surface, sigma x is also equal to 0, because epsilon x is 0. So this is inelastic limit. So the neutral surface this intersects the plane of symmetry along an arc of circle CD. Let me call this, I'll draw another figure. I've got it DE, so I'll call it along an arc of circle DE, and it intersects a transverse section along a straight line called the neutral axis. And the figure to go down with this is that this is the center of curvature C, and we have this bent rod. And this DE is the neutral surface. Arc DE now what we do is we place so DE is our neutral surface. We place the origin of the coordinate system on the neutral axis. Earlier we had placed it at the bottom, but now we will place it at the neutral axis, so that we count everything on the neutral axis, the stress will be 0. Now C here is the center of curvature. Rho is the distance from C to D. So this distance from C to D, we call it as rho, and which is the radius of curvature. So we now place our axis on the neutral surface, and this C is the center of curvature, and the distance from C to D is what we call as rho, the radius of curvature. this angle, if this is theta, so arc length DE this is equal to rho theta, and this is equal to the length of the bar. The original length of the bar was L. So arc length DE, which is rho theta, is equal to L. Now let us look at a section slightly above. I call it as J and K. So the arc length JK, now the distance KE or DJ, this is equal to Y. Because now we are moving up from the neutral axis. Okay. So the length JK is equal to, what will be length JK in terms of rho, Y and theta? It is rho minus Y times theta. So this length JK is equal to rho minus Y times theta. And this is equal to the new length L prime. So change in the length delta L is equal to L prime minus L, and this is equal to rho minus Y times theta minus rho theta. This is equal to minus Y theta. And epsilon x, which is equal to delta L upon L, this will be equal to minus Y theta upon rho theta. Just see if this. We have so far, at one stage I have just said that this is all geometry so far. Stress-strain relations were used just to show that some of the stresses were zero, and at one stage I said this is equal to stress, but otherwise all this argument is geometry based, so it will not depend. As long as M is uniform, these arguments are working, irrespective of material of the bar, whatever. Of course, the area of cross section has been assumed to be constant. So this is what we have for strain. Now the negative sign comes because of positive M, the beam is concave upwards. So when Y is positive, we have a decrease in length. When Y is negative, we have an increase in length if we are going from the neutral axis. So that is why we have the negative axis. So what we show here is that epsilon x varies linearly with Y. Now, once again, we are interested in failure. When will the beam fail? Now, beam will fail when the stress is maximum. For stress to be maximum, strain has to be maximum. So now we try to find when is epsilon x maximum. So, and it could fail under tension or compression, those strengths are the same. So therefore, we look at modulus of epsilon x, and when is that maximum? This is maximum when Y is the largest. So we denote the largest Y as C. So then the maximum strain will be equal to C upon rho, because epsilon is equal to Y upon rho. So, epsilon maximum is equal to C upon rho, and this gives us the relation that 1 upon rho is equal to epsilon m upon C. Now, epsilon x, we showed this was minus Y upon rho. So, this implies epsilon x is equal to minus Y upon C times epsilon m. So, basically we are just working out things. We have, wherever it is maximum, we are writing it as a ratio at any point, as a ratio of the stress there or strain there to the maximum. And so, this is what we get. And now, in the elastic case, so now we use the fact that we use the stress strain relations here. In the elastic range, sigma x is equal to E times epsilon x. So, therefore, E times epsilon x is equal to minus Y by C E times epsilon m, or what we will get is sigma x is equal to minus Y by C times the maximum sigma, where sigma m is the absolute now sigma x varies linearly with distance sorry, let's get back to this again. So, what we get is that sigma x varies linearly with distance from the neutral axis. It is proportional to y, so that it varies linearly. Now, what we know is integral sigma x dA is equal to 0, because there is no axial force acting on a section, we only have a moment. So, this implies minus Y by C sigma m dA is equal to 0, and or minus sigma m by C, which do not depend on anything, times Y dA is equal to 0. So, what does this tell us about the neutral axis? Y is the distance from the neutral axis, and we get integral Y dA is equal to 0. When do we get integral Y dA is equal to 0? When we take Y about the centroid of the area. That is how you get the centroid of the area. Integral Y dA is 0. So, that means this, because Y is being measured from the neutral axis, the neutral axis has to pass through the centroid of the beam. Okay? So, this, so far we had just assumed there was some neutral axis. We did not show where the neutral axis was. But now, if there is no force acting on the bar, no axial force acting, then, which is the case when we have pure bending, then the neutral axis has to pass through the centroid of the bar. So, you locate the centroid, that gives you the position of the neutral axis. Okay? So, what this tells you is, this implies that the neutral axis passes through the So for a case of pure bending, and if we are in the elastic range, if we are not in the elastic range, then there could be y square or something like that. So then that will not be true, but for this case, what we have is this. And we also have integral minus y, sorry, just a minute. Integral minus y sigma x dA is equal to m, and if z axis coincides with neutral axis, then integral minus y sigma x is equal to minus y by c sigma m dA is equal to m sigma m upon c. We substitute in the value of sigma x, which is linear with y. There is one y already there. When we take this, we get a product, integral y square dA. Everything else is a constant, so that can be pulled out. So what we get is this total moment is equal to sigma m upon c integral y square dA. Integral y square dA is nothing but it would be the moment of inertia. It's y square. So it would be iz, because you are taking it about that section. So second moment of inertia I, and so based on this, what we have is sigma m is equal to m times c by I, and sigma x at any section, this is equal to minus m times y upon I. क्या हुआ कुछ? Anything you want to share? मैं वहां से असाइनमेंट पहले ही ले लो उस वाली रो से वहां लगता है बहुत ज्यादा चल रहा लगता है कुछ. Anyway, so we have sigma m and sigma x given like this. Okay. So now these are what are called as elastic flexural formulae. And you can see that sigma x is compressive above the neutral axis, it is tensile below the neutral axis, and this is the form which it takes. Now you see, we have this term C upon I. Both of these depend on the geometry. What is C? The maximum value of y. And I also is something which has got to do with geometry. So what we have is, what we define is, since both of these are, we define I upon C as the section modulus, and what we have is sigma m is equal to m divided by s. So, higher the s, lesser will be the sigma, isn't it? It's obvious sigma m is good. So, what would you like? You would like, if there are two cross sections, which will be a stronger cross section? A cross section where s is bigger, because that means in that cross section, maximum stress for the given loading will be low. So, you can this thing. So, that's why we write it in terms of S section modulus. If a section can take more load. An example is, suppose if we have two rectangular cross sections, now for a rectangular cross section, I will be given by 1 over 12 bh cube, and C is h by 2. It's obvious, it's the distance. So, therefore, if we work it out in terms of area, it's area times h by 6. So, okay, and if areas are equal, so then you would like h to be higher for a given section, so that you have a stronger beam. So, this is how, and we will see some of these problems of this. So, h here for m sub z, h is the y dimension and b is the z dimension. Now, there is only one more thing we need to do, and then we will look at some problems or some more details. The deformation of a member caused by M can be measured by curvature of the neutral surface. Curvature is defined as 1 over rho. And from what we have seen above, 1 over rho is equal to epsilon m upon c, and in elastic range, epsilon m is equal to sigma upon e. So, 1 over rho is equal to sigma m upon EC, and this is equal to 1 upon EC times sigma m, which is equal to MC upon I. So, in terms of the moment and the properties of the material, what we get is 1 over rho is equal to m upon E. So, that is what gives you how much will the curvature be. So, given the member and the material and the geometry of the beam, you can find how much the curvature. So basically, if we look at the formulas, there are three formulas. Two are these flexural formulas which tell you how sigma goes with m and I. Sigma m is equal to mc upon I. Sigma x is equal to minus m y upon I. And the third thing which we have is this one. 1 over rho is equal to m upon ei. And with this, basically, they are the ones with which we can then solve most of the problems. Okay. So we have already seen what the now the structural beams, since there are many standard shapes, this is called there are many nomenclatures of these beams. These are standard shapes. And actually, a lot of these shapes, etc., they are tabulated. And in a lot of earlier designs, when structural engineers used to do the design, they would look at those standard tables rather than doing the calculations at that time when calculators were there, but maybe the computers were not there to sort of feed things in and get the data. So therefore, you'll find, and even in your textbook, if you go towards the appendices, you'll find many of these beams and their properties. So their section modulus and their I, etc., centroid, all will be given there. Then there are other beams like of this shape, or this is an L-shaped beam. This is a C-shaped beam. Okay? Yeah? Well, it's called as a W shape, I think, because probably two of them were put together and one side then. I would rather call it an H-shaped beam, but I think these names have come from some. That's why even these are the standard names in which they are written like this. I don't have an answer to your. L and C, of course, are obvious. Why is this called W? Okay. Now, there's a small this thing. We have a beam being curved like this. What we have seen is that there is a Poisson's ratio, which means if we have an extension in the x direction, in the y and z direction, there will be compression. That could take place. So, if we try to look at a beam in pure bending, epsilon x was given by So that means there is a strain in the y and z direction. Now, if you look at the z direction, that means while the beam is curved like this, if I look at this section in the z direction, then in the z direction also there will be a curvature. And the top part, which is decreasing in the x direction, in the z direction it will increase. So therefore, there will be a second curvature which will come in the beam, in the plane, and what will happen there is that there will be another center of curvature here, C prime, which is below the beam, which will tell us how much the beam is curving in the z direction. Okay, and this radius of curvature, this is will be equal to rho divided by nu because of this relation of Poisson's ratio, and this is called, I think, anticlastic curvature. So the beam, we are not going to look, I just wanted to introduce this to you to show that, just to tell you, while the beam curves like this, there's a slight curvature in the z direction also, but at least as far as what we will be solving, this will not be of much significance. It could be of use later, maybe if you're doing something more advanced, that there's a, so there is something like a saddle type of a shape. There's a curvature like this, and in the other direction there's another curvature. So that is what we are trying to tell you. Okay. Now let's look at a problem so that we try to understand. So we have let me see if I can get this figure somewhere in the if this is here, I'm not sure. Let me try to see if this figure comes in. I don't even have it here. Pure bending. Let's see if they have done the. Okay, this figure is here. So this is, I'll write this problem, I'll come back, but just for the figure part, I'm showing it here. There is this T-shaped beam whose dimensions are given 90 millimeters, 20 millimeters, 40 millimeters. So it's like two rectangles. Okay. And this is connected to the wall there, and a moment of 3 kilonewton meters is acting on this, which is trying to bend it about the z axis. So the bending is, it will tend to bend it outside the plane of the paper. It's about, rotation is about this, no, it will bend it out. How will it? It will bend it downwards. Okay? This is the problem. I'll talk of these numbers, or maybe we can just. A cast iron machine part is acted upon by a 3 kilonewton meter couple, knowing that E is equal to 165 GPa and neglecting the effects of the fillets, that means just assume these to be full rectangles, determine the maximum tensile and compressive stresses and radius of curvature. Okay. So this is the problem, and I'll come to the solution of this. Since I could not have drawn this figure so nicely, that's why I've shown the figure here. Is this clear? Can I cut it and take it there? Okay. So I'll now go back to my notes. So we have, sorry, कहाँ गए नोट्स उड़ गए क्या पूरे? यार क्या हुआ? आज फिर पूरा लेक्चर उड़ गया क्या? Don't tell me. Looks like it. What? I think this is the second time this is happening, but today it is happening at the end of it. Anyway, the video recording will be there, so you can see it from there. I have to get to be more tech savvy about these things. Maybe somebody can help me after the class. So we have the cross section of this bar is in this T shape as I showed in the figure. I have represented it by just a line on the right side on which a moment m is acting. Okay. Now the dimensions given are, this was 90, this was 20, this is 40, this is 30. And you have to find, m was given as 3 kilonewton meters, and we had we have to find maximum tensile and compressive stress and radius of curvature. E of the material is given as 165 GPa. Okay. So now, in problems like this, and that's what why I wanted to do this, was that we basically make a table. We write section 1, section 2, and so let's call this is section 1, this is section 2. So the area of section 1 is 20 into 90, area of section 2 is 40 into 30. Y bar for this is, if we start from the bottom, y bar for this is 50 and y bar for this is 20. So then we calculate y bar times A. So 50 into 1800, 20 into 1200. Now, so first thing which we have to do in a problem like this is to get the neutral axis. So that is what I am trying to do here. Given the area, I am trying to locate the centroid. So if there are 2 or 3 areas, you make a table write the area of each of those areas, choose a reference line, let's say the bottom, get y bar for each of those areas, and then multiply y bar times a, and then y bar will be equal to sigma y bar I ai So this will be the total y bar, and for this problem when you work this out, this will turn out to be 38. Now be careful about the units. Everything is given in mm, so therefore it will be mm4 and area is mm4, y bar is mm, so that will be mm cube, whatever it is. Now the key point here is, for each of these sections, the formula which you have, bh cube upon 12, that tells you the moment of inertia about its centroid. But you have to now shift it to y, to this area, to this thing. So therefore, if you make a column for I, now here what will happen is, if this is 38 mm, so if I draw this picture here of this center here, so this is C1, this is C2. C1C is equal to 12 mm and C2C is equal to 18 mm, because this C is 38 mm. Okay? So therefore, when you calculate the i's, you have to calculate bh cube upon 12 for that rectangle, plus area multiplied by 12 square and area multiplied by 18 square. So these are the type of things. So it's nothing, they're simple calculations, but it just, so this will be equal to 90 multiplied by, what are the dimensions, 90 and 20, 90 multiplied by 20 cube upon 12 plus 1800 into 12 square. And for the second one, it will be 30 multiplied by 40 cube upon 12 plus 1200 into 18 square. And once again, the units will be what? Millimeter to the power 4. So you add up these two. When you add these two, that will give you the total I, and then you can work out. Maximum tensile stress will be at the bottom, maximum compressive stress will be at the top, and rho is m by EI. So after this, it's just formula based. So all the problems actually, once you realize the geometry, are just calculations. You have to be careful and calculate them carefully. Take care of the units. There are lots of to the power of 2s and to the power 4s, etc., which you'll have to work out, but the problems are quite straightforward. Okay? So this is how you can then solve these problems. Now, in the next class, we will talk of composite beam. If there's a beam made up of two materials, same cross section, but there are two materials. So we'll talk of mainly rectangular beams. Half of it is one material, half of it is one material. Then how do we tackle that? So that I'll look in the next class. So now, as I told you, let the quiz be there as it is on Monday. I think some of you said there's some festival, etc. कोई बात नहीं, जल्दी सो जाना एक दिन उस दिन. Anyway, prepare अभी से कर लो, festival तुम्हारे होते रहेंगे. It's a simple quiz. In fact, as I told you, I'll not even include torsion. So basically, it will be tensors, and then The second part after tensors will be more circle, the stress transformation, and then finding stress forces in members, chapter 1 and chapter 2, elongation, and finding compatible deformations. 3 questions, simple questions. As I said, quiz basically is just to ensure you're regular. So we will have it next Monday. I will not be here, but they will conduct it. It's supposed to be 45 minutes. So we'll start at 8:15. I will request all of you to come and please sit with a gap of 2. We have enough room here. The class is only 150. This is a capacity of 450. So by yourself, you'll have to sit with a gap of 2 and people will come and take care of the quiz. Okay. Bring your calculators for the quiz when you come. We of course have a class on Thursday also. कल की क्लास हमने मना कर दी है, नहीं होगी. I will be in my office from 5 to 6 tomorrow. If you have any questions, you want to ask anything, you can come to me and ask.
लास्ट वाले में आपने वाई बार कहाँ से निकाला था? वाई बार क्या?
वाई बार मतलब ये इस वाले का जो है,
हाँ